Pediatri Diacono is going to be here. He has worked on choice of college major. Another local from here, John Cannon, worked on individual migration decisions. What is the region I'm going to work in? There's also a discrete choice. So, that's a long, long list. And essentially, you can think of this as like versions of Heterogeneity. Even like, optimal replacement of kidneys, right? We're going to talk later about equilibrium trade in automobiles, so that's where we're going. So we have this paper where we're modeling the Danish households' decisions on whether to keep their car, trade it for another one. If they trade it for another one, it's going to be a new one. It's going to be type 1, 2, 3, or Volvo or Ford or whatever. So that's where we're going. And of course, there's a lot more, okay? So this is the citation count for John's paper. I didn't update the figure, but it's a pretty high I-squared. So I would say this is like the structural parameters, right? These are policy invariant. And you can just predict. It's like a constant growth in structural econometrics since that paper. It's in many other good papers. Okay, so here's a model. We got a binary choice, replace or not replace the engine. And then Heterogeneity, he looks at the mileage of the bus. That's the observed state variable like Bob talked about. He looked at that, okay? And that's the key state variable, right? Because it affects the cost of maintaining the engine. Presumably that's going to be increasing. If you have like an old clunker bus, it's just have to go to repairs all the time. So that's one state variable. Another state variable, well, that's your epsilons. They are observed by Heterogeneity, but not by me. Okay, so this is the epsilons from before. Okay, just like taste shifters, idiosyncratic shocks to replacement decisions that make Heterogeneity, for unobserved reasons, choose something else. Okay. Got a utility function here. It's here's the utility, or the payoff is the negative of the cost. He's going to be minimizing the cost of maintenance cost and replacement decisions. So if he keeps the engine, well, you just have to maintain all the various parts of the bus, and that's costly. So you have to pay C. C is a function of X, the mileage, presumably increasing. And we would like to know how much is it increasing. So we would like to estimate theta 1, the structural parameters. Okay? Now, if he replaces, there's a replacement cost, another parameter we might try to see we can estimate. Okay? So that's the potentially observable component of utility. And then you got these additively separable I at extreme value shocks. They're going to be I at extreme value, but I haven't told you yet, but now, we're getting there. Okay, so we're going to end with logit formulas and so. Okay, so the state variables, well, they're going to be, the epsilon's going to be following this conditional density. And the mileage process is like this. So essentially, if you replace the engine, well, the current value of the mileage is going to regenerate to 0. Okay? And otherwise, buses just take, drives exogenously every month, and then they come in for repair. He looks at the value of the mileage, and then depending on whether he replaces or not, that has effect on the mileage on the engine next period, because it's, Rust is assuming that, if you replaces the engine, it's just as good as new. Okay? So this has parameters as well. These are the parameters of the state transition process. We might also estimate those because we have data on mileage together with the replacement decisions. So bottom line is we want to try to see if we can estimate the structural parameters, RC, theta 1, the parameters, the utility function, and parameters of the state transition process. Okay, well, we already, he's forward-looking, maximizing future expected utility, yaga, by Bellman's principle of optimality, just like Bob said, we're going to have a Bellman equation. Okay? I mean, and here it is. So you're going to make these discrete choices, 0 and 1, maximize current utility, the sum of current and future expected discounted utility. And here you got the expected value, and you got it right here, right? So it's like, you need to take expectations over the evolution of the state variables for next period, which is going to be comprised of mileage, or the observable state variables and the unobservable ones. So we're going to integrate those out. Okay, so that's pretty hard. I mean, if you look at, maybe not for this particular model, but if you look at it, right, X here, potential continuous state variables. What do you do about that? Well, Rusty just discretized the states. Yeah, it's only one state variable, so maybe it's not, the biggest problem because, that was not the 9,000 combinations, 9,000 by 9,000, that was a lot. Here we had just like 100 combinations, okay? Different values of mileages. But even though you have the small set here, you also have the epsilon, which is a whole continuum of values, right? And if you think about not maybe Harold-Zucker, but like a discrete choice model with J alternatives, and J is going to be large. Also, when it comes to the equilibrium model, it's going to be like 100 choices. So you can easily have more with migration decisions for various different regions you move to, or various different goods you choose between. So there's going to be an epsilon for each of these choices. And so now you got a J-dimensional integral. Oh my God, so what do? Okay, so that requires evaluating high-dimensional integrals. And evaluate, even if you were to compute that by simulation, break Cartesianity by integration, you still have to evaluate the value function in all these potential values that X and epsilon can take. So that's a high-dimensional object, okay? And that requires high-dimensional integration or interpolation if you want to solve for this guy. And then it's non-differentiable. So, Bob talked about, just maximize the likelihood function, right? But now the likelihood function is non-differentiable because it depends on conditional choice, all these choices that has all these max operators. So what do? Okay, this is what John did, and in some sense we have seen this already, so I'm just going to go fast here. And I have 100 slides, so don't freak out. There'll be plenty of material to talk about. Okay, so we assume additive separability of that epsilon. Okay, we assume conditional independence, just like Bob told us, like this controlled Markov decision process for the state variables factors into these two terms, where the epsilons, well, the current value of the epsilons has no effect on the future value of the epsilons other than through those optimal choices and observed state variables. So once you control for X, you don't need to control for the current value of the epsilons. You can't have like zero correlated errors or anything like that. And then we're going to assume at extreme value, like coming from Dan McFadden's supervision, I guess. Okay, so what does it give us? Just to wrap up, it allows you, the conditional independence and the additive separability allows us to really separate the deterministic part of the out of the problem. So you can specify these choice-specific value functions, and then there will be this little epsilon added, right? So just like we just heard, okay? That's a benefit, right? Then you can, and that's what I'm going to talk more about, you can reformulate the Bellman equation in a different space, okay? Don't have to work with a Bellman with a value function that are a function of both X and epsilon. You can work with the expected value function or the integrated value function, or smooth value functions, where those epsilons would be integrated out. And then you can easily get conditional choice probabilities and expected value of the max once you impose this ideal extreme value errors, because then they get in closed form. So you totally avoid most of the problems we talked about. So this is why we're doing this. Okay? So just quickly, okay, so it allows you to, reformulate the DP problem under additive separability and conditional independence in this particular way. It's very clear to see here that, well, you got something here that you have a parametric functional form for, and then you have something here that really not depend on epsilon because that's integrated. That only depends on the observed state variables and the observed decisions. Okay? Because this is what we're conditioning on here. And then you got the added epsilon. So this is the choice-specific value function, if you will, this thing here. Okay? So you're back to the situation where you have like an additive random utility model, looks like the static logit models, if those epsilons are at extreme value. And that's what John did. Okay? And then you can move on and say, now we can reformulate the Bellman equation on a much reduced space. You can work with the expected value function that I call EV, which is a function of the observed states and the discrete decisions. So that's the conditional expectation of that, conditional on X and B. Definition is right here. And now, if you look at it, you got here your Bellman equation here in terms of the expected value function. What do you have on the right-hand side? Well, in here, that's the value function, but in here is the expected value function, okay? So it's really just a mapping from the expected value functions to expected value functions, and that's where you want to find a fixed point on, okay? You want to solve that equation. That's just much, much easier, right? Because, given that, John showed this is a contraction mapping, so it's going to converge by value function iterations or successive approximations, okay? But it's much lower dimensional because it does not depend on those J-dimensional shocks, okay? That's pretty neat, okay? Another way to do it is just another reformulation of the Bellman equation is to look at it in, some people call it integrated value function space or smooth value function space, where you work with this conditional expectation of the value function just given X, so we just integrate out all those unobservables. Okay, so it looks like this, and then we get another version of the Bellman equation here, which is a mapping from this integrated value function to the integrated value function. Now, it doesn't even depend on the discrete choices, so it's even lower dimensional. Again, it's if the original Bellman equation is a contraction, this is also a contraction. Okay, so you can use VFI, successive approximations, your good old plain vanilla algorithm. You guess on the integrated value function, you put it into the Bellman equation, right there. It returns a new integrated value function. That's your approximation of that value function. You stick it right back in, iterate until convergence. And since it's a contraction, we know there's a unique fixed point, and that sequence of successive approximations is going to take you to that fixed point. Very, very nice. Again, lower dimensional. Okay, so the extreme values, well, we've somewhat seen it already. The expectation of that max, once you have that distributional assumption, is very, very easy. So, that expectation would require some sort of, J-dimensional integration, but we don't need to do that because we have the log sum, was coming out of that extreme value distribution, and so we can express those expected max operators in closed form. It's really, really, think of the alternative, J-dimensional integral, and quadrature is a no-go, maybe some simulation, but then you get all the numerical difficulties that follows. Conditional choice probabilities, very easy. You get mother logit, okay? So this is huge. It's like it's like, Dan McFadden and Harold Zucker, right? These are like the great mentors of John Rust, right? Think about Harold Zucker. He would know how to like grease the engines, right? And Dan McFadden knew what the grease was, right? So, there you go. You got your empirical engine all smoothed up with locate shocks. Okay, so we put all this stuff together, and then we're soon ready to do the nested fixed point algorithm. Now we got the conditional choice probabilities here. They are locate form. Have the locate form. We have a nice closed form expression. You got your utilities. That's easy to compute, right? You have a parametric functional form. Maybe it's a linear or quadratic or some power function. And then this expected value, well, oh my God, in order to compute that, you need to compute the fixed point. Okay, so if you look here, how do you do that? Well, you do the successive approximations or whatever algorithm you have to give you, to try to find that fixed point. But see, parameters here, okay, I'm not good, I think. Parameters here, that's going to change what's on the right-hand side here on that Bellman operator, right? So because it changes utility, changes also how we compute those expectations because they affect the state transition process. Okay, so parameters, they affect the Bellman operator. So that's why we index the Bellman operator here with the structure parameters. You change structure parameters, you get a new Bellman operator. Well, if you change the Bellman operator, you also get a new fixed point, a new expected value function. So a result of that is that that expected value function is an implicit function of those structural parameters. And so that's why I kind of marked them with a little subscript theta here. Okay. Well, yeah, we're just going to discretize Meilerich. Okay, 100 different bins, or 175, I think John is using, or 90. Okay, and then that also discretizes the state transition distribution to look like something like this, the conditional, the state transition matrix. If you keep the engine, well, then with some probability you stay in the same bin. With this probability you move up one bin, and so forth, right? So you can estimate this from the data. Now, if you replace the engine, well, you will regenerate the value, the initial value of Meilerich to 0. So regardless of whatever Meilerich you have today, you're going to end up with, with the same distribution of Meilerich tomorrow. So these are just the, state transition matrices conditional on the choice for the discretized version. Okay, and then we can write it in matrix form. Very easy to program. Okay, so now we're ready, almost ready to do the nested fixed point algorithm. In some sense, you've heard about it already. But here's the likelihood function, right? The likelihood is going to be, the log of the likelihood function is going to be summing over all those individual buses, all the likelihood contributions for each bus. Due to the conditional independence assumption, it simplifies. Okay, so it looks like this. So there's two components here. There is the log likelihood contribution for the observed sequence of replacement decisions D, okay, that we assume we have data on, okay, for all the different buses over time. And then there is a log likelihood contribution for the state transition process. Okay. Meilerich this period, next period for all the different buses. This is easy, right? We can write up the likelihood function in closed form, so I'm not going to talk about that. Okay. This guy here, well, that depends on those conditional choice probabilities, which in turn depends on the on those expected values, and those are also implicit functions of the parameters. So what you do is you want to maximize this guy here, the likelihood function with respect to theta, okay? But then every time you change theta, you have to change theta here in the utility function in here, but also recalculating that fixed point. Okay? And that's what the nested fixed point algorithm does. Okay? It imposes the model every time you evaluate the likelihood function. Okay, so since this is, the Bellman operator is a contraction and there's always a unique fixed point, it implies that these expected value functions are also implicit functions of theta, and the resulting conditional choice probabilities are also implicit functions of theta. So you can solve this as an unconstrained optimization problem. So what did John do? Well, he just maximized this guy here with respect to theta using some gradient-based solver. I'm going to talk later about some of the details of that. This one is called the BHHH algorithm, like one of my favorite ones. It's like Bertel, and Hausman. They say, look, this is a likelihood function. Okay, we know, the second order derivatives of the likelihood function in expectation is equal to the outer product of the scores. So that's really nice, right? Then we'll only have to differentiate once. So that's really powerful. And then there's an inner loop. Well, we talked about how to do the successor approximation, or VFI, but there's an alternative, right? You can use Policy iterations or Newton iterations, and that's what John originally did. And it's actually pretty powerful because these two have different properties. One is converging linearly, and the other one is converging quadratic, so really fast once you get to the domain of the solution. Once you got that built up, you can estimate the model. And look, we got replacement cost. Okay, it's 11.72. You got the slope parameter here of that cost function. So every time you move up one bin, it's more costly, right? More older buses are more costly to maintain. Okay? Here's the parameters, the theta 3 parameters. Those are the state transition that tells us how much is the bus driving every month. Okay? So these are the parameters right here, right? Okay? So he did it. And so he did that both for like a dynamic model and for comparison also a static model, beta equal to 0. Okay? But look, you look at the replacement cost relative to the size of the slope parameters. It's very, very low, right? Because, if you were to rationalize why this non-forward-looking hero sucker would ever want to replace an engine if it doesn't get anything out of it tomorrow, those costs would have to be low, right? Okay, so that's hero sucker's model, okay? And see, there's actually code to do that in the repository. And I'm an old guy, so I'm doing MATLAB, but what can you do? So, is this visible? Probably not. Okay, so there's two repositories here, right? Or in the repository, there's two sets of code. I can't see anything here. Code, right? So I'm going to look into this one here, Circular MATLAB, and there's a README file, and you can check out what's in there. I just want to, show you that if I say run bus data, and you can go in and, change specification and so on, it does it, right? So code is working. And it did it actually pretty quickly, okay? It took, I don't know how much time, fractions of a second. Okay. Let's go a step further. Anyway, you afterwards you can do predictions from the model, counterfactuals. And what John did was that he calculated the equilibrium distribution of mileage of those buses that conditional on replacement and non-replacement, okay? And you can do that once you have estimated those structural parameters, right? You got a full specification for what those conditional choice probabilities are and what those state transition probabilities are, right? And together that gives a state transition for this controlled Markov process, okay? And then all you got to do, if you want to find the equilibrium distribution, is to find the ergodic distribution to this control state transition matrix that you got here. That's finding another fixed point. Looks like this, okay? Okay, so here's the mileage for the buses that are not to be replaced, and here's the mileage for the buses that are being replaced. Well, look, from this, you can also calculate demand for engines, right? Because you just integrate that distribution out, and then you got your equilibrium demand for engine replacements. And that's what you see you get right here, okay? And then this was monthly data, monthly incision, so you multiply by 12. Get the demand for engines as a function of replacement cost. Well, now you can have the demand for a given value of replacement cost. You can trace out the whole demand curve of bus engines or other assets like cars or other things we are trying to estimate demand for. And that's this curve here. And you see here, it's done both for the dynamic model and the discrete model, for the dynamic model and the static model. Looks like consumers are much more responsive to changes in the replacement cost you have here on the x-axis. The demand is falling more rapidly, higher elasticity. Okay. That's a model. Okay. You can use it for, like, see what is the counterfactual predictions of mileage demand if you start to tax cars and stuff like that. Okay, so that's Heterogeneity and the nested fixed point algorithm. So it says here, and sorry for this typo, it's 2012, okay? Kenjad and Chilin Su comes and say, hi, why do you want to repeatedly solve all these complicated fixed point problems over and over again? Why don't you just solve the constraint optimization problem? That's what they did. They had this paper in Econometric that is implementing a constraint optimization version of that maximum likelihood estimator. Okay? So you maximize the likelihood function subject to the constraint the Bellman equation needs to hold. Okay? Now there's going to be more variables in the optimization problem. These expected values, well, it's a function, but we discretized it, so it's these 175 different values of the expected value in all the different grid points. That's the variables, the additional variables in the constraint optimization problem. And so they're considering two different implementations of this. One is based on actually pretty nice software. It's called Ample. It's like very high level programming language suitable for solving constraint optimization problems, a little bit like GAMS, you know that. Okay? Okay. And then they formulate that and pass it to a solver, and there could be various solvers. One is Nitro, there's ConOpt, and other solvers. It does automatic differentiation. Okay, so you just formulate the problem, and then it still figured out what is the derivatives of the likelihood functions, what's the Jacobian of the constraints. All that is done automatically by automatic differentiation. Provides sparsity patterns for those Jacobians and constraints and so on. So say, why don't we do this? There's also a version in MATLAB. This doesn't have the second order derivatives, so it's going to be slower, and that's one of the points I'm making. So why don't we do that with Heterogeneity model? It's kind of, you come up with a new estimate or a new algorithm, you have to try it out on that paper. So they take the empirical design from that table I just showed you, right here, all those numbers here, that's the data generating process, okay, with those parameters. Okay, got 175 grid points, linear utility function, these are the parameters. Then we solve the model, simulate data from the model. And then we do Monte Carlo. So they do like 250 Monte Carlo replications and do a horse race between the nested fixed point algorithm and this mathematical programming with equilibrium constraints, or MPAC. And here you go. Here's the main table of the paper. Okay, look at MPAC, Ample, very fast, 0.13 seconds. okay? And they are also counting, how many times out of those 212, they are doing 250 Monte Carlo replications, but they have different starting values 5 times, so it's like 5 different, 5 times 250, that's 1,250, okay? So bullseye, always working, that's 1,250, okay? So it works most of the time pretty efficiently, okay? And if you're very beta, the discount factor, you see also that it's not really affected by that. But look at the nested fixed point algorithm. Well, it's not always working, and it's slow, 24 seconds to solve this model. Okay? And it gets worse. Almost 2 minutes to estimate this model with the nested fixed point algorithm. Huh? Why is that? Because you have to do all these successive approximations, like 748,000 successive approximations to solve, to estimate this model, right? Because you repeatedly need to solve a fixed point, and each fixed point requires several iterations. And it gets worse as beta goes close to 1. You might ask, okay, why am I even talking about the nested fixed point algorithm? Is that a dinosaur method, or is it a completely waste of time? Well, I have a little bit of a recipe to how to speed it up. Okay, so I'm not going to talk so much about MPEG, more about the nested fixed point algorithm, the things you would like to do. Okay? Is there a question? No. In the code that you just ran, what was beta there? Beta was 0.999. 4 nines. Okay, so it's going to be even worse. And so you might ask, how could John do this in 1987 on an old computer with this, this MacBook Pro couldn't do it in 2 minutes with a discount factor that's 0.995. Okay, we got like more nines. Yeah, okay, maybe they didn't do everything. Okay, so here's the CPR for the nested fixed point algorithm. Okay, first, always read the documentation, okay? So that's step 1. You need to recenter logit formulas and log sums, make sure you have numerical stability, okay? Use this Pauli algorithm, which is a combination of successive approximations and Newton's method, okay? So you don't really have to repeatedly do all those successive approximations. Then also calculate analytical gradients of the Bellman operator. Well, we can do that now, right? Because now we added the logit grease. So everything is smooth and differentiable, and we can use the implicit function theorems to calculate derivatives of the Bellman operator and the fixed points and so on. And also subsequently the log of the likelihood function. That's what I'm going to show you, and many of those details are going to be the same also for bigger models, which is just easier to show with Herosucker. And then there's a BHHH, which is just using the outer product of the gradients as approximation of the Hessian. Okay, so, you read documentation. Okay, so read the paper from 87. There's also a documentation manual, and I think the first one was from 87. Okay, I just have the one from 2000, and it's in the box or on GitHub. And then we have a little comment here to that paper, so you can also look at some other. How do both methods compare in terms of precision of the estimates? Well, they're implementing the same estimator. It's a maximum likelihood estimator, okay? So if it converges and, with numerical precision, it's going to produce the same thing. Okay? So it's just 2 different algorithms to obtain the same estimator, the maximum likelihood estimator. I hope that answered the question. Okay, here's more from documentation saying essentially, well, you could do NPEG, but then in the documentation manual says, why don't you want to exploit the fact that it's a contraction and that the fixed point is an implicit function, so you can do the nested fixed point algorithm. So John thought about this 35 years ago. Here's the algorithm. And I recommend you print this out. You fold it a couple of times, put it in your genes. You always have this nested fixed point algorithm on you. It says, okay, here you're going to start. Okay, start with some initial value of the expected value function, like 0 or something, and some guess on the structural parameters. Okay, now with those set of current estimates, you do a contraction iteration, right? Do contraction iterations, iterate on the Bellman operator, again and again and again, until you're kind of sufficiently close to the solution so that the error bound is really small. The difference between two successive approximations is small. Okay. Then, once you do that, you calculate the derivative of the Bellman operator, which is what you need to do this Newton's method. I'm going to show you. It's just an overview. Okay? And then you iterate on that. But that has quadratic convergence, so it's really fast. And then once you're done with that and you got your fixed point nailed to machine precision, you end with the algorithm with the derivative of the Bellman operator, which is in turn giving you the derivative of the fixed point, and then you just use the chain rule and so on to get the derivative of the likelihood function. And then you're ready to go to the hill climbing algorithm and maximize using your gradient-based solver. Wonderful. Okay, need to recenter our logit formulas to avoid numerical instability. I'm not going to talk about that. So here's this is the guy, right? This is the good old plain vanilla V of I. You start with a guess of the value function, give you a new guess, and you just repeatedly continue, and then you could continue. And if you're patient enough, contraction mapping properties is going to guarantee that you find that unique fixed point, you're just patient enough. But it slows down as beta gets close to 1. Okay? Because you got linear convergence. Unlike Newton iterations, where you just reformulate this original problem, right? You just subtract this to the left-hand side, then it should be equal to 0. And then, finding zeros of equations, what do we use there? Newton's method. So here you got, you want to find the zeros on this operator here. And so what is Newton's method? It says, okay, here's my current guess. This is where I am. This is my the derivative of the system of equations I want to put to 0, and then the operator. Okay? So, but it does include this derivative, and it's a derivative with respect to a change in this expected value function. Maybe it sounds a little bit hairy, but it's not hard. It's really easy, actually, to code. Cool thing is, now, instead of having linear convergence in the error bound, you're going to have quadratic convergence, which means as you get closer and closer and closer, these errors are just going to race to 0 with a quadratic rate. Okay, so here's what I mean. This is successive approximations. Okay, you got tolerance. Okay, boom, 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 boom. Not much is changing even after 50,000 iterations with beta equals to 0.11. And the relative size of these two tolerances is going to be equal to the discount factor. Okay, so it's slow. Here's a graph for different discount factors, okay? With 0.95, well, we don't need that many iterations to really get to a small error bound. Right? Solution arrives very quickly. Makes a lot of sense, right? I mean, you're trying to approximate an infinite horizon problem with, finite sequence. I think it's like a finite approximation to an infinite horizon problem. And so if people are not caring so much about the future, well, maybe that approximation is pretty good. Whereas if you go up here with 0.99999, okay, it's going to take forever. Okay, this is John's discount factor, or Heterogeneity discount factor, 0.9999. Even after 10,000 iterations, we're not nearly close to machine precision. And it matters, because if you're doing numerical gradients to calculate what the derivatives of, say, the likelihood function would be, then you don't want those changes to appear because now you just took like another couple of iterations, right? You get too much noise, right? You really need to nail this. Okay. Here's a log of the error bound. This is why you can see it's called linear convergence, right? They're all linear and the slope is equal to a discount factor minus 1. Okay, but we have the Pauli algorithm. Okay, we do a couple of contraction iterations. This is right here, right? These are the contraction iterations. Okay, and then we say, oh, now we close. So we do Newton-Kontorovich. That's these. Okay, I said I had quadratic iterations. Look at the tolerance. It's 10 to the power of minus 2, minus 4, minus 8. And then at some point we are battling with the precision on the computer, okay? Which is roughly 10 to the power of minus 16. Okay, and look at this. Pretty fast. Huh? Quadratic convergence, very, very fast as you get into, if you're close at the solution. So here's a few words about when to switch to Newton. And it's not hard to show that if you say you nailed the value function, like say Harris-Zucker's value function, well, it's going to be decreasing in mileage, something like this, right? You got the curvature right, but it's just shifted down by the constant or up. This little k. Now you do a successive approximation, it's not going to delete that constant. Okay? It's just going to be there. 1 minus beta times a constant. If you do another one, it's still going to be there. It's just going to be multiplied with beta. And now you can see it's going to take time, right? It's going to take many iterations if that constant is big and beta is very small. Okay? But if you do Newton, it's just going to strip that constant away, right? There's no constants when you take derivatives. So that's really cool. So that's what you do. First, successive approximations, and then Newton-Kontorovich. And look, if you take the relative size of these two tolerances, right, it's actually equal to beta. But what about, right here, you saw it converged to beta, those relative tolerances. So once you reach that point, you know that you're close to that situation where you just have a constant, or you have a good idea that that's the case. Okay, so do some successive approximations until you get relative tolerances that are very close to the discount factor. Then you switch to Newton. Okay, so here's the implementation, okay, in this simple model, some MATLAB code, choice-specific value functions, okay, and here's the derivative of the Bellman operator, just one line of code. Okay, so I'm going to skip that. Now I talked about, this is step 5, right? Analytical gradients of the likelihood function. That's what we want to maximize using our gradient-based solver, right? Okay, you need to calculate derivatives to use Newton's method. Well, it's easy, right? It's just applications of the chain rule and the implicit differentiation. Gradients, we're working with the Login model, so it's going to be the gradients of the likelihood function with respect to a change in, say, a utility parameter would be the usual one, right? It's going to be the difference between the indicator for replacement or the discrete decision J minus its choice problem. It's a little bit like, the residual from the discrete choice model, multiplied by the derivative of the choice-specific value function. Like, if this was a static Login model, this would be like, with linear utility x times theta, it would be x, right? And you have the explanatory variables would have to be, independent of the residuals, right? Okay. Anyway, so, but this is the choice-specific value function. How do you calculate that? Well, we just take that partial derivative. The first part is easy, right? That's just derivative of the utility function. Second part is more involved. You got beta, and then you got where is the choice-specific value function? Somewhere back here. I'm not going to go back, okay? But trust me, it's going to be the choice-specific value function times the derivative of that integrated value with differentiated with respect to those structural parameters. Well, this is easy, right? But this guy here, we can compute by implicit differentiation. So here's the formula. The indicator, not indicator, the identity matrix, and then derivative of that Bellman operator. Well, we already know that, right? We got that from the Newton-Kantorovich. That was what we needed to calculate the derivative of the Bellman operator to find the fixed point using Newton. So it's like a byproduct of the solution algorithm. Okay? And then you just need to calculate the partial derivative of the Bellman operator with respect to a change in the structural parameters. Okay? And we just combine those things. 1, 2, 3, you're done. Easy peasy. Okay? Does it matter? Yeah, it matters, because what is the alternative? You know, numerical calculation of gradients and numerical imprecision. And of course, nowadays, you know, Python packages like JAX is going to do automatic differentiation for you. You would have to help it with the implicit function theorem, but all this other stuff you don't have to think about. Huh? But I got the formulas here. Okay, BHHH. There's your Newton-Raphson, right? This is your starting values of parameters. This is step size inverse of the Hessian times the gradient, okay? This, you know, the sum of the scores over all those observations. But we only talked about the first order derivatives, not the second order derivatives, right? Only know how to differentiate once. Of course, you can do it again. It's just cumbersome, right? So why don't we just use the Berndt-Hall and Hausmann, replace this outer product of the gradient with the Hessian, approximate that with the outer product of the scores, is totally valid from the information identity, because the expectation of the negative of the Hessian is equal to the expectation of the outer product of the scores. Of course, this holds if model is well specified as n go to infinity, at the true parameters, yaga, 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 but in reality it works pretty good most of the time. Okay. Another benefit is, look at this. This is like the score square, right? So it's always positive definite, which means that you always go in the direction of the gradient. Okay, so you're always going to go uphill, even in the areas where it's convex, like here, right? Here, the standard Newton would just, you know, take you further and further away from the max of the likelihood, whereas over here, it would be okay, but not with BHHH, because, you know, you always go in the direction of the gradient, always uphill. So that's really nice. Okay, so there are some advantages and some disadvantages. You know, like I said, only a good approximation when information identity holds. Okay, so this is a bit business advice from the sitting president. Oh, not the sitting, sorry. You know, we don't know if he's going to, yeah. Okay, let's move on. I don't want to look. Okay, and we got convergence, and we have a runtime. It was not 2 minutes, because we did all these things. So I think my main message here is that some of these tricks here, even with the old methods like the nested fixed point algorithm, if you do that, right, it's going to make the difference between whether you can estimate an interesting model or not. Implementation matters. If we redo the Monte Carlo, well, so here's MPEG ample. We were able to speed it up. We probably have newer computers. So it's like 0.1 second before. Now it's 0.06, so pretty fast. And NFXP is equally fast. Okay, so it's not such a bad idea. Okay? And it's easy to understand, right? It's also very robust. Look at the times it converged all the time. It's because the contraction mapping ensures that you always find the fixed point, right? You may go to a Newton-Kantorovich iteration and it takes you to the wrong place, but you can always go back to successive approximations and then eventually you would get into the domain of attraction. So Bellman equation can always be solved, okay? And then it's all about maximizing likelihood functions of a logit, which is pretty easy once you got that. Okay, yes?
Question.
Yeah.
So when you do Newton, you always have to keep track of inverting that big matrix. Now, in Rust, you give us a very simple. Sorry.
Yeah. Good point. Okay.
Yeah, so
I was not trying to shove that over the rock, so it's a great question.
Okay.
Now, look at the.
Can I finish my question so that people
Yeah.
can understand it? So the question is, when you do the Newton, you always have to invert that big matrix.
Yeah.
At some point, the cost advantage of doing the Newton is going to diminish, and then MPAC or other methods like that will start to, that do not require that.
Sure.
Will be better.
Sure.
Right? So at what point is that starting to be a concern?
When models are big, that is when the state space is big, the number, here, what do you have? Like 175 grid points, which means that derivative here, this guy here, the derivative of the Bellman operator, that's going to be 175 by 175, okay? If you have more states, it's going to be bigger, of course, right? Like the 9,000 case before, it's going to be 9,000 by 9,000. Oftentimes these are sparse and they are easier to compute. But MPAC also have to compute that derivative because it's a Jacobian of the constraints, so there's no way around it if your alternative is MPAC. Of course, here there is a trade-off. If you're doing successive approximations all the time, you would not have to do that again and again. So I don't want to give you like the answer with 2 lines under. You have to do so many successive approximations, and then for depending on the model. But it is when the discount factor is relatively low. Well, you can do with successive approximations, right? And you entirely avoid Newton iterations. Yeah?
Related to this question, I would say that I would add as part of the CPR of the nested fixed point algorithm, I would say that in this Newton-Kantorovich iteration, never invert directly this matrix, but use a solver of system of linear equations, and especially a solver that can exploit sparsity matrices.
Yeah. Good point. Yeah. Okay. So, with that said, let me check how much time do I have left? I spent almost an hour. Okay. Let's talk about the other part. Okay. This is like Harris-Zucker with more buses. Okay. So it's equilibrium trade in automobiles. And here, this is going to be a secondary market, but we don't observe the prices at the secondary market. So we would have to compute those from the equilibrium of the model. So there's going to be an additional nesting here where we repeatedly have to compute the equilibrium, where you get supply equal to demand for all the different types and vintages of cars to back out those prices. Okay? That's why we call it the doubly nested fixed point algorithm. So I'm going to go through that now. Okay, this is joint work with Fedor and Anders Munk Nielsen from Copenhagen, and John and Ken Gillingham. Okay, so we're going to go to Denmark. It's pretty expensive cars in Denmark. Okay, so what's the price of this? Well, it's more than $200,000. Okay, so cars are very expensive in Denmark. And the comparable price for that vehicle is around $60,000 here, or was, because it's not on the market anymore. It's still an expensive car, right? It's like have the full shebang with leather seats and massage seats and everything, right? So, but still a very expensive car. Why? Because we tax cars a lot. At this time, at the margin, the registration tax you would pay on a new vehicle would be 180% of the marginal kroner or dollar. And then on top of that, you pay 25% value-added tax, so you pay tax of the taxes. And you can see here, this is not the Volvo, right? It's a Toyota Aventus. You see here, Denmark, very expensive, okay? Most expensive cars in all over Europe, although before taxes, they are cheaper, okay? We are not looking at the incidence of this tax. We don't have a producer side or anything. That's the next paper, okay? So we're just assuming 100% pass-through if we're making tax changes to this model. Okay, car taxes does generate a lot of revenue in Denmark, 30 to 50 billion Danish kroner, divide by 7, I guess, to get it in dollars. 2 to 3% of GDP, 4 to 7% of total tax revenue. Okay, so it's a lot of money because we already tax people. And so the question is, are we doing this optimally? And before we answered this question, we thought maybe we should just have a model before we try it on humans. Okay, so that's a goal. We want to have a model that can answer the question: should we change the balance from registration taxes to, for example, road user charging or fuel taxes? Okay, here's a preview. The registration tax is over the top of the Laffer curve. You can actually reduce taxes and increase tax revenue. And even more, you could also increase consumer welfare and reduce CO2 emissions because people will drive their cars less intensively if you reduce registration taxes and tax the fuel. That's what we find. Okay, so here's a model. We got cars. Cars are not, they're heterogeneous by the type of the car, J, 1 up to capital J cars. And then there's going to be different ages because you can always also buy used cars. A is going to be equal to 0 if it's a brand new car, but the state variable can never be more than 1 or less than 1 because you can't wake up in the morning with a brand new car. So that's the cars. And so they initially sold as new in the primary market, then traded in the secondary market, the used cars, until they eventually scrapped, something that we also model. Okay, so there's a range of different choices consumers would make. The driving decisions, I come to that later. That's how many kilometers to drive. But they also make purchase, replacement, trading, and scrap its decisions. They infinitely lift, maximize expected discounted utility, and we're going to add extreme value shocks so it all looks like a hair circle. In fact, they're going to be generalized extreme value because we have a nested logit structure. And so the addition here, compared to what we just went through, is that's going to be an equilibrium where supply equal to demand for all these used vintages of cars. So for each of those used cars of different ages, of different types, it's going to be prices and quantities denoted by this ownership distribution Q. That's what we do. Okay, so here's a roadmap. We're going to do like John, maximize the likelihood function, search over the parameter space, and then there's going to be an additional loop, an equilibrium solver. For every value of the structural parameters, okay, we want to put excess demand for all cars equal to 0. Okay? By changing prices, that gives us the equilibrium prices and quantities. Okay? But in order to calculate excess demand, we need to solve the dynamic programming, the consumer problem. Okay? So that is like this. For each trial value of those prices, we solve the single agent problem. Based on those discrete choices, optimal discrete choice, we can derive conditional choice probabilities that in turn tells us about how the state evolution of the cars is going to be. Okay? So we can compute the state transition matrices with something we called which is composed of the trade transition. That is how the cars are changing hands, like the musical chairs, and then the aging of the cars, which is denoted by Q. And then we go and calculate that ergodic distribution, just like John did, by finding that ergodic distribution to that state transition, which is now a function of the prices, right? And that allows us to evaluate the excess demand. So the plan is to go 1, 2, 3, 4, and then we'll see how far we get. Okay, still have a little bit of time. Okay, it's just weekly, okay, the specification of utility. Okay, so utility here gives utility of car services. They're going to be decreasing as a function of the car age to reflect, essentially decreasing utility. You just don't like the smell of old pizza in your car, right, as it gets old. Okay, and then increased cost of maintenance, stuff like that. It's a function of the age of the car and also the type of the car. Beyond that, there's a monetary cost of operating the car, like how much fuel do you have to put on it. That's going to be different across the different types of cars, right? Some are more fuel efficient than others, and these agents also make optimal choices of how much to drive, so people are going to sort into different cars depending on their driving demands. And then there's going to be the trade and transactions cost. If I put a car in the market, right, and sell it, my trade cost is going to be negative, right, because I get money in the bank. All this monetary stuff is multiplied by mu, which is going to be the marginal utility of money. Guess what? It's going to be heterogeneous. Okay? So we've got heterogeneity and marginal utility of money and other parameters in here. Beyond that, you got your epsilons, which is going to be generalized extreme value to allow for correlation between alternatives, and that gives us nice nested logit formulas and conditional and analytical expressions for expected max operators that are log sums of log sums of log sums. Here's the choice tree. This is a consumer choice tree for someone who has a car. Okay? So you wake up in the morning with a car, and then you decide, oh, should I keep it? If you keep it, there's no more choices to make. Just wait another period and see, okay, it's getting older. You can also get rid of the car. We say purge the car. In that case, you have to think about, okay, now what do I do with my old car? I can sell it or I can scrap it. Okay, that's a decision that depends on the price at the secondary market and the scrap price, which is something we endogenously solve for. And then you can replace a car for another type of car, like, a big car, small car, electric vehicle, and so on. You make your own categorization of cars. And then once you decide on the type of the car, you have to decide on should it be a new car, a 1-year-old car, a 5-year-old car, 7-year-old car, 25-year-old car. Okay? Once you found your new car, well, it's a replacement problem, right? So you get rid of your old car again, and then there's the scrap its decision and sell decision again, like a nested choice. That's a choice tree. So I'm just going to slowly go through the Bellman equation. Yes?
Just a short question. So if I want to also think about investment into the car. Hi. So just thinking about the original problem and the bus engine and sort of investment or maintenance, could I just model this as replacing the car with the same car prime?
Yeah.
So that's
yeah, you can buy the same car again and again and again, that same type of car.
No, I mean I would replace the car with itself and some additional investment in it. So I would kind of repairing the car.
So you want to repair the...
exactly, yeah. I'm thinking about repairs here.
That would just add more choices to the model.
Yeah, exactly. It makes it
I'm
bigger.
not saying it can't be done, but it's just... actually, I had a master student doing that in a PhD, in a master thesis. Based on this model. It was not cars, it was houses, and you could do repairs, and that would change, say, the age of the house. Okay. So we're just not doing that here. Okay. Here's the value function. Okay. So you got all these three groups of choices: keeping the car, purchasing the car, and then replacing the car. If you keep the car, right, this is the choice-specific value of keeping the car, which is going to be here in the next slide. I'm going to come back to that. Okay, and then there is the purchase decision, and here we mark purge or no car, choosing the no car state as like the empty set. It's not like a type of a car that has a number, it's an empty set. Okay? It's like remind ourselves there's no car. Okay, and then there is the choice-specific or the group of choices that you have over here, the replacement cost, which is the max over the types and the ages and the scrappage decisions. And all this have additively separable generalized extreme value shocks. States are in green, so you wake up in the morning with this type of car, and then you make these different choices. So let's go through them. So here's the first one. This is a choice-specific value of waking up in the morning with this type of car, IA, okay, and then purchasing it. If you do that, well, you get utility of no car because you don't have a car, you just got rid of it, right? And then this guy here, he's choosing scrap. So his monetary part of utility here, these trade costs, is going to be the scrap value of the car, right? So that's subtracted. That's right here. Or that's added, right? It's subtracted from the cost. It's added to his utility. And so then he wakes up in the morning with no car, and that's the expected value. The future expected value is his future expected value of no car. Alternatively, well, he puts it on the market, then he gets PIA, which is the price of that car he already had, right, at the secondary market. Okay? Beyond that, there could be like sales transactions cost. He still ends up in the same situation tomorrow, and get the expected value, the discounted expected value of no car. Here's the one that keeps a car, right? So if you keep the car, well, you get the utility of the car, the driving utility of the car that you have, okay, that you kept, but then with probability alpha, it runs into an accident, it becomes a clunger. That's like exogenous scrappage in this model too. Okay? Just things that are outside our ability to explain with the prices. Okay. But with the 1 minus alpha, it's just aging. So A is becoming, the car is becoming 1 year older and it's still the same car. Of course, you know, you could have a choice where you could have a choice that affected how the age transition would be different, right? Or the quality transition would be different. Yes? Okay. If we choose age before type, no big changes in the model. And I need to scroll up here. Comment. I can't read this, so I have to go over here. Thinking of repairs would definitely be an interesting, given the size of tax in Denmark. Yeah, but we don't really have those data, so but yeah, it's interesting. Thanks for the comment. I think I better rush through here. Okay, so where did we go? Now we basically covered most of the choice-specific values, and see here's for the replacement. Let's take the one where you put it on the secondary market. Well, the monetary cost is going to be, you're going to get the utility of the car that you bought, and then you're going to get the trade. You have to pay the net cost of replacing that car, plus potentially sales transaction cost and bias transaction cost. And all these functions here we would estimate as parameters. Okay, now that was just just the choice-specific values, all these guys here, but note, in there was the expected value. So how do we solve this? Well, we use the ID extreme value shocks to represent this model in expected value function space, and now all of a sudden we got the mapping from expected values to expected values. Okay? Because the expected value function is just, this log sum of those choice-specific values that you have right here with the expected values on the right-hand side, so you've got a mapping from choice-specific values to choice-specific values. Of course, they all depend on those endogenous prices. You're going to get a new fixed point for every value of the price vector. So just like the fixed point is an implicit function of the structural parameters in Heterogeneity problem, it's just going to be an implicit function of those prices. Okay? We can get the conditional choice probabilities again by using the Logit formula. And here it's simplified just for clarity. I just assumed everything was ID extreme value. In the paper, there's more elaborate formulas with this nested Logit structure. Okay, with that, we got all the conditional choice probabilities as functions of those prices. So how do you compute the state transition? Well, first let's define what that ownership distribution is. It's going to be a vector of quantities or fractions of consumers holding cars of different ages. There's also a fraction of people that's going to be in the no-car state. Okay, so this is going to be, J times the number of ages of cars plus 1 for the outside goods. So it's just a vector, okay? And so we're going to try to see if we can find that in equilibrium. We assume a little bit more here. We assume that there's an infinitely elastic supply of new cars. So this is we just take those prices of new cars as given. Of course, we can add a supply side, and that's the next paper. And then we have an infinitely elastic demand for scrap cars, and we could also have model the scrap guy, how he set the prices of scrap cars. What we are solving for is those J times A bar minus 1 endogenous disturbance cars at the used car price, the used car market. Okay. So here's the definition of the equilibrium. Consumers maximize discounted expected utility, and secondary market clears for all the tradable cars that put supply equal to demand. And then this ownership distribution Q is time invariance, it's stationary distribution. Okay, so, if you're working with a model where there's a lot of technological development, like, the inflow of electric vehicles, maybe this is problematic, right? But we're working on that in another paper. Or you should work on it. So here's this trade transition matrix. I'm not going to go through all the details of this. Essentially, it just depends on all those conditional choice probabilities we just derived. So here's the probability that I end up with the same type of car next period. Well, that's the probability that I buy the same type of car again, plus the probability that I kept my car, okay? And of course, these are matrices themselves because they're different ages of cars and so on. Okay, so there's no way we can digest this matrix now, but take a look at the paper in this area. The Q matrix is just telling us how those different ages of cars or different types of cars are aging. So remember that with probability 1 minus alpha j, it become 1 year older. Okay, so it's a pretty simple state transition matrix we have here. With probability alpha j, it just goes to the clunker state and becomes A bar old. Okay, but the combined state transition here, where the former here, this trade transition matrix is a function of the prices, that's what gives the state transition for the car fleet. So if we wake up in the morning with an ownership distribution Q, then this is going to be the ownership distribution next period. And then we're just going to do like John did, find the ergodic distribution by finding the fixed point of this equation, which can be, in our case, done with linear algebra. But you could also just do it by successive approximation, starting with a guess of Q, multiply those matrices on and on again and again and again. And we show this a unique stationary ownership distribution secured by those generalized extreme value shocks. Okay, then we're ready to the excess demand. There you go. Here's the demand. Here's the supply. Excess demand is the difference. Let's look at demand. We're going to look at demand for cars of type J of age D. Okay? That's a function of the prices and the quantities, which are in turn, functions of the prices. So what is this first part? This is the choice probabilities, those logit formulas we just derived. Right there, right? The conditional choice probabilities, probability of choosing car type J at age D. This is the conditional choice probabilities. Conditional on the state that I don't have a car, okay? So people who without cars, this is their conditional choice probabilities. How many are there of them? Well, we just look up at the ownership distribution and multiply with that number, okay? So this is the demand for cars of type J in HD for those who don't have a car. Well, there's other people. Maybe there are other people that have cars. Well, they're right over here. Right? And we just sum over all those distributions. We aggregate that entire distribution, use this ownership distribution to micro-aggregate demand using these conditional choice probabilities for choosing that car type J at age D. That's the demand, function of prices and quantities. Supply, well, what's the supply? Again, it depends on those conditional choice probabilities. Here's the probability for keeping the car. This is the probability for scrapping the car. So who's going to put cars on the market? Well, that's the people who are not keeping the car, not scrapping the car, okay? If they had that car. That's the supply of used cars. You just look at, okay, how many people have cars of type J, HD, multiply with the probability that they're not keeping it and not scrapping it, but putting it on the secondary market. Now you got supply and demand, and you just subtract them, and then you got excess demand. All this is a function of the prices, but recall, this was an implicit function of the prices as well. So essentially, the whole thing is a function of the prices. Now you got a nonlinear system of equations you just need to solve. So, given the stationary distribution condition here, that Q here is just a function of those prices, we just have as many equations as we have used cars in the market, and as many as known as we have prices for those used cars. We just solve that system of equations. We show equilibrium exists, and then that was pretty much it. Okay, that was excess demand. Well, we still want to estimate the model, right? We found out how we could find equilibrium prices and quantities, but now everything here depends on the structural parameters. So what we're just going to do, like John did in 8087, do the outer hill climbing algorithm. And we're going to use the same stuff, like the B triple H, analytical derivatives, and whatnot. So to compute these stationary flow equilibrium, that's putting supply equal to demand and finding those prices, again, we can use Newton. Yeah? We can use a gradient-based solver because, the conditional choice probabilities, because of model logit shocks, they're going to be smooth functions. So everything is going to be smooth. Okay? We can use a gradient-based solver. We have like a series lemma that shows that all this stuff is a smooth function of the prices. So excess demand is a smooth function of the prices for a given value of those parameters. We derive all those analytical derivatives, just like I showed you with Harold Zucker. The code is there. And then we get precise, and we have some precise starting values. Okay? So we just repeatedly use Newton when solving the dynamic programming problem with Newton-Kontorovich, when solving for equilibrium prices, when maximizing the likelihood, again, using BHHH with the approximation of the Hessian being the outer product of the gradient. And we just use the chain rule of calculus to build up gradients in a recursive way, just like you would do back propagations if you work with neural nets. Okay. Okay, we didn't talk much about those different types of consumers. So there's going to be different types of consumers like me and John. Because I was working with John for a year and visited him at Georgetown, and I had a really bad FICO score because I'm a foreigner, right? And I don't have any experiments with depth here, so I couldn't lease a nice Mercedes or something. So, but John was nice enough to put this car on the market because he replaced his old car. That used to be John's car, but now he put it on the market and replaced it with this brand new Volvo with leather massage seats and the whole thing. So this is like the rich man's Volvo and the poor man's Volvo. This is what Bob started talking about, right? The heterogeneity results in gains from trade, right? Look at how happy they are. Okay, so it's very easy to add persistent consumer heterogeneity. Essentially, we just, we derive the stationary distribution by solving for all these trade transition matrices for all the different consumer types. Okay, so there's going to be trade transition matrices that are different for different consumer types and different consumer type specific ownership distributions. Okay, which are fixed points to these. Okay, and then the excess demand, well, you just aggregate up all those excess demand for all the different consumers, multiplying with the probability that you are type tau, okay? And so you get something like this. And you see the sorting, you see a clear sorting here. This is the age of the car and the fraction of population who are owning cars. This is like just a little simple example here. You got rich, that's John, and poor, that's me. I'm more likely to buy the older cars, right? Okay. So you got a clear sorting of consumers into each regime, the heterogeneous and the poor consumers are going to be more likely to be in the outside good. Now we increase transactions cost, and she kind of limits that trade. Okay, and it's has also a heterogeneous effects on the two different consumers. Essentially. Here's the prices that come out of the model. The blue one, that's from a heterogeneous consumer economy. That's me and John. The red one, that's where there's only John. And you see the prices are higher, right? Because we trade with each other. And here's the... anyway, maybe I should just speed up and what do we want to show? Then... This looks like a pretty complicated. Yeah, that's what okay, so let's go forward. That's why I just want to use can I use 5 minutes for the empirical application? Maybe I should do that. Okay, so we did this because we were set into evaluating the effects of lowering registration taxes and increasing road user charges in Denmark. Then we used a model like I just described, of course, with many types of cars and ages of cars and different types of consumers. There will be consumer heterogeneity, not only in the marginal utility money, but also in the driving demands and the utility for different cars. And then we used this We estimated the model on the Danish register data, and then we made it counterfactual where we cut the registration of taxes for cars by half and then increase the fuel tax and see what was the effect in equilibrium. And then we computed a bunch of economic, welfare, and environmental implications of all that. To be able to do that, we need to have like a utility specification of driving. It's all static. Essentially, just put structure on different types of consumers, utility for different cars. Okay? And we estimate in the first step all the driving demands and essentially substitute that in. Okay, so I don't have time to go through the details of that. Then we estimated the model on the Danish register data, and what this slide says is that the model fits pretty well. Here's some predicted market shares for different types of cars. Here's the actual market shares. They ought to be on the 45-degree line, and we're happy about that. This is the actual and predicted probabilities of purchases. Blue is the data. Okay, so more there are more trade of new cars. Here's the observed ownership equilibrium distribution. This is almost like Q, except there's something called the post-trade distribution. Okay, so it's not the ownership distribution, it's the distribution that happens right after the musical chairs. Okay, this is the observed one. Okay, and you see here different, the different colors is different combinations of consumer types and so we have 8 different consumer types in this graph here. So this is like a low work distance couple that is poor. This is a corresponding person that is rich. And you see there, the rich ones are more likely to buy the new cars. Okay? This is what you see in the data. The model also predicts the same thing. Okay? So data, model, okay? So we're happy about that. Here's just another way of looking at the sorting. This is observed sorting, this is the predicted sorting. We get the equilibrium prices out of from the model, and if you compare those two prices, or what can you call it, like depreciation rates from the Danish Automobile Dealer Association, they are actually pretty close to what they recommend to the auto dealers. Then we do the counterfactual, and we're going to do several types of counterfactuals. One where here's a baseline with the different registration taxes, the existing registration taxes from 2008. Then what we're going to do is we're going to do a counterfactual where we change those registration taxes and find the budget balancing fuel tax. Okay, but we use a model where we just assume that prices are changing proportionally. Just the used car prices changing proportionally, just like the new car prices would change. Not the equilibrium response. That generates a huge excess demand for a bunch of different cars, like people just replace those cars too often according to that price. Then following that, we say, okay, what happened in reality if you calculate the equilibrium following that? That's what we call naive realized, okay? And then there's a sophisticated policymaker who use our model to predict what the prices or what the consumer responses and prices and quantities would be. Okay, so here's a total tax revenue, okay? By construction, here it's budget balancing, so it's going to be the same. But if you see what happens if you don't base a policy on the equilibrium, well, there's going to be a big hole in the Danish budget, okay? And so, what is this saying? Well, it's saying that, see, when you look at the expected age of a car, it's just way too small because people are replacing those cars and buying specific types of vehicles too much. They're not taking adequately into account how the prices should change in this market to ensure supply was equal to demand. In fact, the average age of the car would be higher in reality, okay, even higher if you change registration taxes and fuel costs in the optimal way. Here's our Laffer curve. Okay, so we changed the fuel tax and the registration tax. This is the status quo. So you can see here, if you were to increase the fuel tax, you actually, the car tax, the registration tax, you decrease tax revenue, but if you decrease it, that is moving this direction, right? You get a higher tax revenue. So we're over the top of the Laffer curve in Denmark with 180% tax. Okay? Here's the CO2 emissions of new car registration and fuel taxes. Okay? Well, of course, if you make a car more expensive and more expensive to drive, people's gonna pollute more and drive more. Okay? So it's not so surprising that if you reduce those taxes, moving into the picture, then you get a higher CO2 emissions. And here's the social welfare excluding those costs. This is the consumer surplus, if you will. And we can put all this stuff together in this final graph, and then I'm going to shut up and let you go for lunch. Say, okay, here's a baseline. Here's the total tax revenue contour curve of the Laffer curve, right? This is this curve here, right? It's like a contour curve here, okay? Then you got the contour curve here, this like constant welfare, okay? If you reduce taxes, you're gonna get higher welfare. And then the last one, that's the constant CO2 emissions. Okay, so if you increase taxes, you're gonna get lower CO2 emissions. And so there's this sweet spot, this green area, where you can get everything. Higher tax revenue, larger welfare, and lower CO2 emissions. Isn't that nice? Anyway, that's it. I'm gonna stop here.